see the review video on our YouTube channel. Okay, now let's get started. Let's review what we learned. Let's start from 4A. We spent almost more than 3 weeks on chapter 4. So in 4A, that's the first section of chapter 4, and we kind of try to build a bridge between kinematics and kinetics, right? So that equation we used in 4A is basically just Newton's law. Sum of forces equals ma. Notice that I have all forces and the acceleration in vector form. So that tells you this is a vector equation. That means this equation could be breakdown into 2 directions, either x, y, or I or j. And the usually question type under section 4A gonna be ask you to find out what's the force. So that's kind of the give you some hint to let you know, okay, maybe this question I need is from section 4A. It's chapter, has a lot of similarities, something are overlap with each other. And sometimes you may get confused and don't know which section you need to use to solve the problem. So if you see a problem that asking you to find the force or acceleration, there will be a good chance that could be a problem from section 4A. And we did some examples, like if you have a block is connected with a pulley and there's another block. And so in section 4A, we're only look at how forces or acceleration changes at a single moment in time. So we do not change time or change position in 4A. We only look at a single moment. That makes sense to you. If that also gives you a sense like when would be a good time to apply at just F equals ma from section 4A. Okay. So next that's about 4A. That's pretty simple. And 4B, in 4B, we start with the equation of integral of sum of the forces on ET direction, ds, equals 1/2 mv2 squared minus 1/2 mv1 squared. And so in 4B, when you look at the equations, and we did some changes to this equation and to find the work energy equation, right? And on this set of equation, this is work done from some forces. On the right hand of the equation, this is change of kinetic energy. Then, so we usually use big U, to see this is work done by forces from position 1 to position 2. Or we can call this as total force, and equals on the right hand side of equation, kinetic energy can be written as T, right? T2 minus T1. Now, if we look at this total work done into the system, this total work done can come from two different parts. We learned there are two different types of works can be done from the forces. And if you have conservative forces, recall what are the conservative forces, right? Most of the forces are conservative forces. Only remember if you have friction force is a non-conservative force. So if you have gravity or spring and those conservative forces, then the work done by the conservative forces can be, let's use just C, UC, and the work can also be done by non-conservative forces. Let's call it UNC. Okay, then like we mentioned, if you have conservative forces, then the work done by the conservative forces can be written as change of potential energy. So this term here can be further broken down to V2 minus V1. And those V's are potential energies, could include the work done from the gravitational force, the gravitational potential energy, or spring potential energy. And for the non-conservative force, and that's just would be the friction force, ds. If the direction and the magnitude of friction force doesn't change over the path, then this can be written as just friction force times the path of the friction. And overall, we can define our work energy equation. That's the most important thing we learned in 4B. Work energy equation equals T2 plus V2 equals T1 plus V1 plus the work done from position 1 to 2 from non-conservative forces. So that's the most important equation we learned from 4B. But keep that in mind, this non-conservative work done by non-conservative forces is here, right? It's come from here. But where is this part, the work done by the conservative forces? And actually they're in a different form as V1 and V2, which is already built in our work energy equation, V1, V2. And also our kinetic energy, T2 minus T1, or T2, T1, they're also in the equation. Okay, so the question type in this section gonna be ask you to find what are the distance and what's maybe how far something travels or moves. And it could ask you for what's the deflection or stretch on spring, and what's the change of height if you have a pulley to pull a block, right? That's delta H. And what's the path? What's the travel distance? Oh, we mentioned that. And it could also ask you to find what's the speed and what's the maximum spring stretch. What's if system here, just to side notes, if a system is released from rest, what does that mean? That means all the masses in the system at the beginning at position 1, if it is released from rest, the speed of all the masses are equal to 0. Equal. Yep. And if what if like the problem tells you, okay, the spring is stretched to its maximum length? What does that mean? If sometimes it tells you it's a maximum stretch or length, that also means everything stopped from there, right? So you couldn't stretch anymore. So that also indicate at that position, V equals speed equal to 0 as well. And another thing I want to mention is this work energy equation. If you look at all the components here, I don't have that vector notation for them. So this is a vector equation. Oh, sorry, scalar equation. Okay, and let's go back to the question type here. And another way a problem could from this session is ask you what's the work done from something. Work done maybe from friction or from gravitational force, stuff like that. For example, friction. So those are the kind of indicators you could use work energy equations. Okay, and a good example for problems from 4B could be we have a multiple mass, let's call this A, this B, and are connected with pulleys and ropes, and it has some springs in the system, and there's friction on the surface. I could add another pulley here and add another spring here. Okay, so a system like that, if we can, let's call this C. If we add at the beginning, this spring is compressed, and now if we release the system, release block C from rest, and how would everything move? And then problems like this, you can use work energy equation to find out what are the potential energies, what are the kinetic energies, and is there any non-conservative work done from the system? Because, for example, this one, we have 2 springs, right? And you probably know we should probably have a potential energy from either of the springs at a given position. Also, this block here has this high difference than other 2 blocks. So it should have a potential energy, depends where you set your reference for 0 potential energy. If you set your reference here, then this block C would have negative potential energy. And also, since if we have surface friction, then you would need to consider the work done from the friction, which is a non-conservative force. That's the last term in our equation. And a few concepts, make sure you understand is when we talk about potential energy, so if potential energy is from gravity, this potential energy from gravity can be, that equation goes g h, right? H is the height from the reference point to where's that your mass. And the potential energy from gravity can be positive, can be 0. It could also be negative, right? And then how about the potential energy from a spring? Could potential energy from spring be both positive, zero, and negative? If you look at the equation for potential energy from spring, that is 1/2 k delta x squared, right? And k is the spring constant, delta x, that's a deflection of spring, and it has a square there. So spring constant is always greater than 0. So only if there's no flat deflection, otherwise you always have the spring potential energy greater or equal to 0, right? So it's non-negative. You can't have negative potential energy from spring. And also we have the work done by non-conservative forces such as friction force. So for those type of work and the energy done, the work done from friction, it's always less than 0. Only if you don't have friction, then that's 0. But it's if you do have friction, that work is always 0. Less than 0, sorry. So it's negative. Make sure when you have non-conservative force from work done from friction, make sure you always add that negative sign there for friction force. Okay, and another thing we have in the equation is kinetic energy. Kinetic energy equation can be written as 1/2 mv squared, right? So it's pretty similar with the spring potential. Nothing can go negative only if you have a negative mass, which is not the case in our class. And so that tells you your kinetic energy would also greater than 0. It couldn't be only if it could be greater or equal to 0. If it is not moving, then it could be 0. If it is moving, it has to be greater than 0. Okay, that's about section 4B. And so next, let's look at section 4C. In section 4C, we did a little bit modification on F equals MA, and then we end up with integral sum of forces dt equals m v2 minus v1. And we're back into vector equation again. So from A, B, C, only section B, it's a scalar equation. Both A and C are vectors equations. And on the left-hand equation, we call this as our linear impulse. On the right-hand equation, we have this is called linear change of linear momentum. So here I stress linear. That's because in 4D, what we learn is called angular momentum or angular impulse. That's why here I add linear to show you in 4C, we're talking about linear impulse, linear momentum equation. And everything is vector. So if that is vector, that tells you this equation can be break down to at least 2 directions, right? If you have I, J, or you have other directions. And something we mentioned is if you have sum of the forces, for example, equal to 0, x direction, that implies you have conservation of momentum. only on x direction. And if similarly, if you can have sum of the forces equal to 0 on y direction, that implies the conservation of momentum on y directions. But if you only have sum of forces on x direction, you cannot get a conclusion that conservation is momentum is conserved on y direction. It has to be on the same direction. If that makes sense. So the question type in this section for C where we ask you to find what's the duration delta t, what's the speed or velocity, and what is the average force, what are the momentums. So here for this average force, if they ask you to find either average tension, average force, and that means you can simplify the integral of sum of forces to just force average times delta t. Okay, and one example we did in 4C is, remember the two boats, a tug, and tug is towing a boat. And what we did is we can look at these two boats as a system. Then you can do analysis, draw free body diagrams to find out the speed, how both A and B are moving. So when you look at them as a system, then you ignore the internal forces, right? So when you look at them as a system, we don't look at the tension force in between them because that's considered as an internal force. But if we want to solve what is the tension in the cable, then in the rope, then we need to look at just one boat. Only look at one boat. In that case, in your free body diagram, you will have the tension force there you are able to calculate. So let's look at just 4A. Okay. That's it. That's about what we did in the first part of 4C. But in section 4C, and there's another topic. So 4C, that's impact. So we talked about impact problems. So in the impact problem, the equations are similar. Right. Let's use F A V E delta T equals M V2 minus M V1. So the equation are very similar with the first part of 4C, but here for the impact problem, we assume if that is an impact problem, this is how we identify if that is impact problem. This delta T going to be very small. So that leads to, we're going to end up with a fairly large force, impact force here. And remember the impact problem, the example we did, we start with two particles, A and B, they impact with each other. And first thing is you need to identify where's your T and N coordinate. So we have this line and this line, the perpendicular. And this line here is T, that is a plane of contact. and another length n, that is line of impact. Then we start with just particle A. We start with particle A in class, oops. Just for A. Then we end up with a conservation of momentum on T direction. Then we look at just B, we end up with a conservation of momentum on T direction. Then we start looking at A and B together. Then we get conservation of momentum on N direction. And the fourth step we did for that impact problem is we used the coefficient of restitution that is also on the N direction. So if you look at, go back to look at the notes, you'll realize the first two parts are both on T direction, and 3 and 4s are both on N direction. And 3 and 4s are more useful than, I wouldn't, they're both very useful, but most likely you're going to use 3 and 4. And for this coefficient of restitution, and keep that in mind, the definition has that negative sign in front. And you, on the top, you have VBN2 minus VAN2. The bottom is VBN1 minus VAN1. And we also mentioned two cases for this coefficient. When E equals to 0, that means they stick together. If T equals 1, that means it's perfect bounce. And that's when no energy loss. And so those, when two particles stick together after impact, that's a very important information from the problem statement. If you see that, and then you can assume our E equal to 0, then that could help you to solve some of the speed from particle A or B after or before the impact. Okay, then we mentioned this is an impact problem, and there's a very important notice: never use work energy equation during impact. Never use work energy equation during impact. You see that I use during and not, so that means you can use work energy equation before or after impact, but not during the impact. And one example we did on that is we have a very complex curve. At the end of the curve, there's a block, there's a spring, and the particle P is released. Then the particle can travel along the curve. Once we hit this block, compress the spring. Then we break down that problem to 4 different kind of locations or moments. Oops, 3, 2, 4. So from 1 to 2 is when the particle P travels from this height to a different position, and we can use work energy equation to find out what's the kinetic energy, or in other words, what's the speed at that location before impact. And from 2 to 3, that's the time impact occurs. Then we use the concept, there's 4 equations, 1, 2, 3, 4, and you can solve for the velocity or speed of both particle and the block after impact. Then from 3 to 4, that's after impact, you can use work energy equation again to find out how much both block and particle compress this spring. That's the one of the in-class discussion we had. Just one more thing I will mention is, if you have a particle, it's an impact problem. If you have a particle that's traveling in that direction, you have the particle, another particle that is traveling in this direction. So they were impact at a moment, right? And even they, at least one of the particle would have this angle when this of the velocity. Your line of impact and plane of contact will still be the same. So on this direction, there's still be t, and this is your n, which is the line of impact. T is your plane of contact. Since that's pretty obvious, they were contact. This is at that surface. So this plane of contact should be tangent to that surface. And if we call this particle A and B, and as you can see, particle A is traveling with the velocity, it has the angle with either t or n. So that tells you you would need to use trigonometry using any given information. Let's call, for example, that's theta. You need to use that given angle to kind of project that velocity or speed into both t direction and n direction before you using any of those equations. And for the block B, it's traveling t direction, so you don't need to do any modification on that. Okay, that's pretty much what we learned in chapter 4. And just 4D, the topics we learned on Wednesday, angular momentum wouldn't be on your exam, so you don't have to worry about that. So focus on 4A, 4B, and 4C. All right, any questions, guys?